So, uh, as I told you, counters is one more class of the registers, right? Now, what exactly my counter is going to do? It is going to give my output in a specific counting sequence pattern. So, what's a pattern that will be given by the designer? For example, now let us start to design one simple counter. Okay, what do you mean by counter in general? The entity which is designed to count something, I call it as a counter, right? So now, if I look into a counter, basically my counter is can be classified into two classes. Okay, so which are those two classes of counter? Those my counters can be classified into asynchronous counters. This is not a new term for you, right? You have already know about what is synchronous and asynchronous. Yeah, can anyone tell me what do you mean by asynchronous? What do you mean by asynchronous counter? Yes. What is synchronous and asynchronous? What's the difference? What is synchronous? What is asynchronous? Have you not discussed this in the flip-flops? You are
Ma'am,
going the other
asynchronous
way.
immediate change.
Correct. So what happens in a when I call a circuit as an asynchronous circuit? See, we have discussed this in our flip-flops also, right? Synchronous input and asynchronous input. Similarly, we are having synchronous input clock counters called as an synchronous counters and asynchronous input counters called as an asynchronous counters. Okay, so these are the two basic classifications we are having. Now the next question is, what do you mean by synchronous and asynchronous? When I call my counter as a synchronous counter and when I call my counter as an asynchronous counter, whenever I apply a clock, okay, if I get the response immediately as soon as I apply an input. Well, see, remember this terms forever. Okay, when I say it is an asynchronous signal with respect to digital system design, where whenever I say it's an asynchronous circuit or asynchronous system, it means what? It is not having any gate. As soon as I apply an input, immediately if I get an output, then I call it as an asynchronous signals or asynchronous systems or asynchronous circuit. Okay. Similarly, in the counter here also, I apply an input. As soon as I apply an input, if I'm getting an output immediately, then I call it as an asynchronous counters. Okay. Then what is synchronous counters? Synchronous counters are one in which its output is synchronized with the control inputs. Its output is synchronized with the inputs. What do you mean by that? It's not only the input that is going to make my output to change. Along with the input, it's also waiting for something else to happen. Okay, what is that something else? It is some control signals. Okay, so then I call it as a synchronous signals. Okay, so that is the main difference between asynchronous and synchronous. Now the same thing applies even for my counters also. Counters are also called as a synchronous counters and asynchronous counters. Okay, so now to start with, we'll always go, let us start with an asynchronous counters and then we'll go for a synchronous counter. So what's an asynchronous counter? I don't have any other control inputs here. It's only the clock and the input which is going to make me the change in the output. Then I call it as an asynchronous counters. Now let us take an example for an asynchronous counter. Let us try to design a 3-bit asynchronous counter. Okay, so what is that we are trying to design? I'm trying to design a 3-bit asynchronous counter. Okay, so we are trying to design a 3-bit asynchronous counter. Now wherever we are talking about the registers as a shift registers, what was the type of flip-flop I was using there? It was a D flip-flop. Why D? Because it was mainly, what was its application? It was mainly used in a memory part of application wherein I want to store some information. So as I want to store the information there, I want to hold the information there, I was using a D flip-flop. Now what's the role of my registers over here? The registers are used to generate the count sequence. Okay, so what is the purpose of a counter? To generate a count sequence or to generate a specific pattern of the count. Okay, so for that purpose I'm using a counter. No, so what I want, it's not that whatever I input I'll give the same thing I'll be getting at the output. So I will not be using a D flip-flop here. Instead, what's the type of flip-flop I'm supposed to use here? So for that we'll be using T flip-flop. Remember, wherever we talk about the counting applications, it's a T flip-flop I'm going to use. Why T flip-flop? Because when my T is enabled, that is when my input for a T is 0, then it will be in the no state change, no condition, no change condition. And when I apply 1 to my T flip-flop, then it will be in the toggling condition, correct? So this toggling characteristic of my T flip-flop is enabling me to generate whichever a specified output pattern I want. Okay, so for that purpose, we are going to use a T flip-flop. Instead of T, what else I can use? What is an replacement for a T flip-flop? JK flip-flop, right? So I can make use of a JK flip-flop. And in what way? I'll take my both J and K input, tie it together, give it to logic high. So it will be always in a 1-1 state. So when my J and K are in a high state, it will be going to a toggle condition, right? So I should use it in a toggling condition. So these are the possibilities I have. Either I'll be going for a T flip-flop or I can go for a JK flip-flop. In fact, other than this, D and SR can also be used. But in that case, some additional control logic has to be applied. That's all. Okay. So, but to make our circuit simple, I'll be always using a T flip-flop or JK in a T format. Fine. So that's why I'm taking a T flip-flop. Now, what is that? What is my design agenda now? I want to design a 3-bit asynchronous counter. What is my agenda? I want to design a 3-bit asynchronous counter. What is that I want? So as I told, it's a 3-bit asynchronous counter. Tell me what mod counter I have to design now. I hope you remember the terms we have used. State, mod counter, right? Counting sequence. What mod counter I am supposed to design now? What do you mean by modulus? The number of unique states I want to count, right? So that gives me the mod, right? If I say I want m's, if my counter, whatever I have designed, if it is having m states, then I call it as an m mod counter, right? Now I say I want to design a 3-bit counter. Tell me what will be the value of m here? How many unique states I'll generate? Is it 3 states? 3 inputs. I want 3 flip-flops. 3-bit synchronous counter I want to design. So I want 3 flip-flops. Which flip-flops? 3 T flip-flops. Now, these 3 flip-flops together give me how many specific unique states? How many states it's going to generate? What do you mean by state? The outputs what I'm going to get, that I'm calling it a state, right? So 3-bit counter I'm designing. Tell me how many states I'm going to get. Three bits, how many states? It's 2 to the power of 3. 8 unique states I'm going to get as an output, correct? This together makes me a counter. All 3 bits together, 3 registers together makes me one counter. I call this counter as a 3-bit asynchronous counter, correct? When I do that, then what? How many unique states I'll be getting? I have three inputs, so let me call this Q0, Q1, and Q2. So it is Q0 is my LSB and Q2 is my MSB. No, let me take it in another. This is Q2, this is Q1, this is Q0. Okay. So Q2, Q1, Q0 are the three inputs I am having. So Q2, Q1, Q0 are the three inputs I am having. Now in this three inputs, whatever I am having, giving me a 3-bit output. So how many possible outputs are there? So either I should get it as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? These are the states. So how many states I got it altogether? Number of states. So it is 0, 1, 2, 3, 4, 5, 6, 7. Right? So I have taken from 0. 0 to 7 is the number of, is a counting sequence I want to count. And what is the number of states I am having? I have altogether 8 states here, right? So my M is equal to 8, correct? I have 8 states. 8 unique states are there. So I call this as a mod 8 counter. So what is this called? Mod 8 counter. After 8, what happens? Again it starts from 0. Okay. After 1, 1, 1, again it goes back to 0. Roll over. Okay. Again it goes back to 0 and again it starts counting. So I call it as a mod 8 counter. Why? Because I have 8 unique state. And this mod 8 counter is counting what? It's counting from 0 to 7. So what is your maximum counting value? It is m minus 1. Correct? 0 to m minus 1 is the counting sequence which counter is going to generate a counting sequence of 0 to m minus 1? It's a mod m counter. So in this case, I say my m is equal to 8. That means it is going to generate a counting sequence of 0 to 7. Correct? So this is the counter that we are supposed to design. So I want this counting sequence to be designed. Now how do I design it? So as I told you, I have taken a T flip-flop. And now, as I want to design a 3-bit asynchronous counter, I have taken 3 T-bit T flip-flops. And what is that I have done? Now, let us look at the design. I hope we have done this circuit in the last class also, but again I am repeating it to make you understand better. Okay, so I have applied a clock to the first flip-flop. So this is my flip-flop 1, this is 2, and this is 3. Okay. So I have given a clock here. Fine. And what's the another connection I have? I have an enable, count enable. That is a count. This is an input I am giving. Right? I have given a count enable. See, I have given a count enable as an input, which has been given as an input to all my flip-flops. All the 3 flip-flops are having an input count enable. Okay. So all T are connected to one input. This is an input. Let me call that input as a count enable input. Okay. And then what's the assumption to start with? What are the 2 assumptions I have? 2 assumptions to start with the design is, the first thing is my output state. First output state is 0. That is, I have made all my 3 output to be 0, 0, 0. I have started with the state 0, 0, 0. This is my first assumption. What is the second assumption? Second assumption is that my count enable is made 1. What's the second assumption? I have made my count enable is equal to 1. What do you mean by making your count enable is equal to 1? It means that I have made my count enable is equal to 1. It means what? Indirectly, I am making my T to be in 1 state. Okay. So, with these 2 assumptions, we'll start the design of a counter. Now, what is that I am doing here? for a design purpose. See, I have taken three flip-flops. I have connected it vertically. You can even connect it horizontally also, no issue. Okay, so I have connected three flip-flops here, and to the first flip-flop I have given a clock input. Fine, and I have in which state I am? I am in this state. State m is equal to 0. Okay, with this condition, let us start the circuit design. So I have applied the clock input. When I apply the clock input, and you can observe here, I have given a clock only to my first flip-flop. So when I apply the clock input to this, what happens? My t is equal to 1. What was my previous state of Q2? Q2 is the output I am getting from the first flip-flop, no? So what's the status of Q2 to start with? It was 0. So when I apply the clock pulse, what happens? It becomes 1. So I am in this state. 0 becomes 1. And others do no change because I am not connected. Okay, now let us see what I will be doing for the next clock series. What I do now, I have two flip-flops here. Two outputs for my first flip-flop, Q and Q bar. One is called normal output, the other one is called some complemented output, right? Now, this particular counter, what I am designing, a 3-bit asynchronous counter. What's the characteristics that we are having? We are going to design a positive edge. So what's the other attribute I am going to add to my 3-bit asynchronous counter? I call it as a 3-bit positive edge triggered counter, asynchronous counter. What is that? 3-bit positive edge triggered asynchronous counter. I want to design a 3-bit positive edge triggered asynchronous counter. What do you mean by positive edge triggered? Now my flip-flop will not be triggered all the time. It's going to trigger only during the positive edge. Correct? What do you mean by that? So when my count is in the positive edge, only during the positive edge, my flip-flop is going to change. Okay, so it's a positive edge triggered 3-bit asynchronous counter I am going to design. Correct? So now this is positive edge triggered. No, I am applying a clock, so it's a positive edge triggered. What I'll do for the second flip-flop, no, in order to generate the counting sequence, I have to go like this. I have two outputs, Q and Q bar. So what I do now, this Q bar, the output of this flip-flop is is given as a clock to the second flip-flop. So what I have done, the output, which output? Complemented output of our previous flip-flop is connected as an in clock to the next flip-flop. What I am doing in my asynchronous counter, in any asynchronous counter, this is what I am doing. I am not applying the clock simultaneously. I am not applying the clock simultaneously. It's the second difference you have between synchronous and asynchronous counter. What is that I am doing? I am not applying the clock simultaneously. What I am doing? The complemented output of the first flip-flop is taken as a clock input to the second flip-flop. Okay, so that is what I am doing. When I do that, what happens? When I do that, what happens? When I apply a clock, I have applied a clock here. For my first flip-flop, when I apply a clock, for the first flip-flop, during the positive edge, there will be a change in the output, correct? So, Q changes from 0 to 1 and Q bar changes to 0. Now what has happened? So, this is in this state, correct? 0 state. And that is fed as an input to the clock. That means what? What's the clock I am applying here? It's a negative logic is the clock I am applying here. Correct? So what happens to my flip-flop? My flip-flop is not triggered because it can trigger only during the positive edge. Correct? So I am in a logic 0 here. Similarly, what I will do for the next flip-flop also, the negative or complemented output is given as a clock to the third flip-flop. Okay, this is the connection we have for a 3-bit asynchronous positive edge counter. 3-bit asynchronous positive edge counter. Correct? So these are the flip-flops which are going to trigger only during the positive edge. Now what I have done? I have applied an input to the clock T, right? So now let us start analyzing our circuit. This is how the circuit connection will be done. Now what I have done? I have assumed that all my outputs are in zero state. So all the three are in zero state. Now I'll apply the clock input. So what's the clock input I'll apply here? I'll apply a positive edge clock. When I apply a clock here, what happens? My Q2 was in the zero state. It toggles to the one state. When it goes to the one state, Q2 goes to the one state, what will be the condition of Q2 bar? Q2 bar will be in a zero state only. So that zero itself has been given to the T flip-flop, second T flip-flop. So there is no triggering to this flip-flop. So whatever output I had in the previous state, the same output will be carried out here. So here there's a toggling, but here there is a no change condition for other two flip-flops. So in my next state, so in the first clock, so this was my clock I have applied. So which clock I am taking as a reference here? This clock I am taking as a reference. So when I apply my first clock, so what happened? During the positive edge, when I applied my first clock, if I take it as Q2, Q2, Q1 and Q0. So during the first clock, what happens? Initially to start with, I was in the zero state, and this positive edge triggering, what it is doing, it's making my Q2 to go to the one state, right? It's making my Q2 to go to the one state. But what happens to Q1 and Q0? For Q1 and Q0, it's a negative edge. So there will be no change state. So they continue to be in a zero state only. And simultaneously, I'm trying to write the timing diagram also. Okay. So this is what is the condition. Now let us see what happens. Now again, I'll apply one more clock. So when I apply a clock now, what happens? When I apply a clock, okay, so during its positive edge, again I'm applying the second clock. So when I apply the second clock, again during its positive edge, what happens to Q2? Q2 was in a one state. So toggling will make it to go to zero state, correct? So what happens to my Q2? Q2 goes to zero state. Why? Because of the positive edge. It toggles. It again goes to zero state. Now, when Q2 goes to zero state here, what happens to Q2 bar? That will be in a one state. So what happened? This becomes a positive edge, correct? It goes to one state here. So this becomes a positive edge for my second flip-flop. When it becomes a positive edge, what happens to the output Q1? Q1 was in a zero state. It changes to one state, right? So you can observe here, there's a toggling from here to here. It toggles from 1 to 0, going to a negative edge. Now, this toggles to 0 to 1, going to a positive edge. Right? What this positive edge will do now? This was in a zero state, now it goes to 1 state. What? My Q1 goes to 1 state. When my Q1 goes to 1 state, what happened to Q1 bar? Q1 bar is in a zero state only. So, this clock is still in a negative level. As this is still in a negative level, there will be no change from here to here. So, it still continues to be in a zero state only. So, I continue to be in a zero state. Okay. Now, let us apply the next clock pulse. Where? Here. I'll apply the third clock pulse. Okay. So, what is that I'm doing now? I'm giving my third clock pulse. So, I gave third clock pulse. Now, when I give a third clock pulse, what is the zero state here? I was in a zero state. So, I'll change to one state. So, what is this? It is 0 to 1. It's a negative edge. So, as this is a negative edge, what happens? So, my output was in a one state here. So, sorry. Yeah, but it was in a zero state. Now I'll go to one state. So, this is 0 to 1. But what? When it is 0 to 1, what happens to? So, this changes to 1, this changes to 0, right? So, that 0 will again keep this flip-flop as a negative edge. So, my flip-flop number 2 will not be activated because it is going from positive edge to negative edge. So, there is no triggering. So, what happens here? Whatever state I have, I'll retain the same state. There is no change in the state now. My first flip-flop changes from 0 to 1. This 0 to 1 change will make my second flip-flop to not to trigger. It is not triggering now. So, it will remain in the same state. What was its previous state? Its previous state was 1. So, it remains in a 1 state only. So, I continue to be in the 1 state. Okay. Now, as I'm in a 1 state, this my output is 1 here. What will be the output of this? This is 0. As this is 0, what happens? So now I was in the positive. So thus, so this is in the 1 state. So I'm still in the negative edge. As I'm still in the negative edge, there will be no change in my output. So I still remain in the 0 state only. So I continue to be in the 0 state. Now let us go to the next clock. I applied one more clock. Okay, so this is my 4th clock. So when I apply this clock, this is the next positive edge. In the next positive edge, what is happening again? Again, this toggles to 0. So this goes to 0, right? So this goes to 0. So when it goes to 1 to 0, what happens here? So this becomes 0, this becomes 1. So this one will make my clock to go to the positive edge, correct? So what will happen? As it goes to the positive edge, again the triggering happens. Because of that triggering, my second flip-flop will toggle. In which state it was? It was in the 1 state. So from 1 state, it changes to 0. So there's a toggle here. So it becomes 1 to 0. So I'll go to 0 state here. Okay, I'll go to 0 state. Now, when this output becomes 0, this output becomes 1. So what happened to my flip-flop now? So my flip-flop, what has happened to my flip-flop? My flip-flop will go to the positive edge. So this positive edge will make my third flip-flop to toggle. So when it toggles, it was in the 0 state. It changes to 1 state, right? So see, it has changed to 1 state now, right? It has changed to 1 state. So now it goes to 1 state, correct? Now if I apply one more flip-flop, count what happens. So it becomes count 5. I think it is not visible to you. Okay, so that makes again my clock to be positive edge. So what happens to this? This toggles to positive edge, 0 to 1. So when it becomes 1, this will be 0. So as it is 0, there is no triggering to this flip-flop. So there is no change over here. The same 0 will be maintained. And what happens to this? As there is no triggering to this is still in a 1 state. So there is no change. So this same thing will be maintained over here. Okay, so it will be the 1, 0, 1 condition. Again, when I apply the clock, so this again toggles going to the 0 state. So when it again goes to the 0 state, this will be triggered. So that triggering will make that also to toggle. So it will go from 0 to 1 state. So there's a toggling here. But as it's in the 1 state, there is no change in my flip-flop. So it will be in a negative edge only. So no triggering for the third flip-flop. So it will be in a no change state. Right? Again, when I toggle, so I will go from 0 to 1, but there's no change in these two states. So this is how what I'm doing. See, when I see the circuit, I see that with every clock impulse, I'm changing my condition in this format. So the first was 000, next 001, 010, 1011, 100, 101, 110, and all ones, right? So what I did, I generated a 3-bit counter. With every clock I am applying, I'll be keep on counting the value. So if I convert it into decimal, what exactly the counting sequence I have generated now? It is 0, 1, 2. With every clock tick, I'm keep on changing my count value. So it is 0, then 1, then 2, then 3, 4, 5, 6, 7. Right? So this is how I have counted. So I call it a positive edge trigger 3-bit asynchronous counter. Now why I call it as an asynchronous counter? It's because as soon as I apply a clock input, as soon as I am applying a clock input, I have an immediate response in my output. Right? So that's why I call it an asynchronous clock input counter. Now, this counter is also called as ripple counter. Okay, so I can also call this as a ripple counter. Can anyone tell me why I call this a ripple counter? A thing that has been happening here, you can observe here, the output of my first flip-flop is going as an input to the second flip-flop, and the output of the second flip-flop is going as an input to the third flip-flop. So this is called as, this is a cascading, right? And when I call my circuit connection as a cascading connection, if output of one circuit is going as an input to the second circuit, then I call it a cascading connection, right? And what's the effect that we'll be having with the cascading? That's called a ripple effect, right? What do you mean by a ripple effect? What do you mean by ripple effect? Yes. What is ripple? We have designed a binary parallel ladder, no? Ripple parallel ladder. Why I was calling it as a ripple? What is ripple effect? So what do you mean by a ripple effect? Rippling means what? Rippling. Whatever are changes that has been happening in the first stage, that is being propagated to the next levels. It is inhibited to the next level. Okay. So what and how it is inhibited? It is sent in a way in a next layer. That is simultaneously it is not happening. It's happening one after the other, right? So this is an effect, cause and effect. The cause is happening at the first case, flip-flop, and it is affecting the second flip-flop. Okay, so that is called as a rippling. And rippling effect will always leads to a propagation delay. Okay, so this is a problem we have with a 3-bit asynchronous counter. So what's the problem with the limitation of a 3-bit asynchronous counter? It is going to generate a propagation delay. Okay, so in order to reduce this, we'll be going for the next type of flip-flops called as synchronous flip-flops that we'll study it in our next class. Okay, what is synchronous counters, and then we will design one synchronous counter. So that will complete your unit. Any doubts?